this article, we are studying the L'Aquila earthquakes. In particular, we studied in very detail how the earthquake started. This is because looking at the data, so at the seismograms, at the shaking on the free surface that was generated when this earthquake in 2009 started, we noticed that there is a very small amplitude signal that is somehow anomalous, that is not always seen in all the earthquakes. And we wanted to understand what was this signal. So what we did is that we collected data around the epicenter of the earthquake, that is a magnitude 6 that occurred in April 2009. And then we started to look at the very detail of the signal, the initial part of the signal. And we noticed that the length of this first small event was not the same station around the epicenter, so the duration of this small event. So we did some processing to try to understand how this first part of the rupture was behaving, and we noticed that we were able to derive that the rupture is propagating with a very low speed. So this is using, then we used some physical models that describe how the rupture of the propagation of the rupture in a fault is related to the speed of propagation, and this permits us to retrieve that the beginning of this earthquake generated very small amplitude seismic waves because somehow it was struggling to start. So it was consuming a lot of energy before becoming a big earthquake. So this is a great example of like the complexity of an earthquake that is started with a very small, tiny, and like somehow struggling process that somehow consumed a lot of energy and didn't generate a lot of seismic waves. But then this process probably dropped the friction of the fault and it became like a big earthquake, a big devastating earthquake. So generated a lot of shaking, a lot of seismic waves. So this is what we can do by analyzing the details, the wiggles that are recorded near earthquakes, and we can really get to the physics and understanding what is the complexity, what is happening during the earthquakes.